So today we're going to start chapter 2. And chapter 2 is going to start off with a lot of review. Mostly because I thought you needed to know a lot of this before we really even got started with class, and so I talked about it earlier. But we should go over it again and just make sure it's cemented in there before we start talking about the more complicated aspects of chapter 2. So we're going to go through and we're going to remind you about ionic and covalent bonding so that you remember exactly what that is and what the differences are, because it becomes really important here. All your naming is still really important here, and knowing how to identify between each one is very important. Now we're going to introduce Lewis dot symbols in a little bit more of a formal nature. Before we kind of threw them at you and said, this is some really simple ones, this is how we represent them. Now we're going to go through and we're going to do a bunch of very complicated ones that go way more into depth on what exactly is going on, which will lead us into trying to talk about how molecules look like and doing geometries and things like that. Then we're going to do some more Lewis dot structures that are even more complicated. And more Lewis dot structures. Really, chapter 2 is kind of all about Lewis dot structures and getting good at them. Once we've really got that down packed, we're going to go through and do some bond strength and length comparisons so that we can see how they're related to each other. So, again, some review from last time. So bonding is all about trying to figure out how to complete octets or make things more stable than they were. Now you can do that by, in something like this case, sharing electrons. If two different electrons have 6 valence electrons, they can go share them. They can take 2 of their electrons, share them with each other, and then form some bonds there so that they each can have 8. There's our 3 main types of bonding. We have our ionic bonding, our covalent bonding, and our metallic bonding. Remember, these are important for knowing how to name them because we use different names for our ionic than we do covalent. And they're very different from each other. So in ionic, you're trading an electron. Sodium says, hey, I have an extra electron. And chlorine says, well, I don't have enough. And so the sodium gives its electrons to chlorine. Sodium becomes a 1+. Chloride becomes a 1-. They share the electrons, or they switch the electrons. Now, that plus and minus, well, now they're attracted to each other. They're like little magnets, right? So they're going to be attracted to each other, and that's how that bond forms. Now, something that's covalent, on the other hand, they're going to share the electrons. So something like carbon monoxide. Carbon and oxygen, both of them don't have quite enough electrons. So if they share some of them, now they can each have what they need. And so they're kind of stuck together by the fact that they're sharing the electrons. Now, we need to know how to differentiate between the two, right? So the way that you decide whether something's ionic or whether something's covalent is, for right now, seeing where they are in the periodic table. So if something's on the right-hand side and the left-hand side are 2 different things, like sodium and chloride, you have a metal and a non-metal. That means that you're going to have an ionic bond. Something that's covalent will be 2 nonmetals, so everything up in that top right-hand corner of the periodic table. If it's made up of things over there, that's going to be covalent. Now, this is a little bit of an oversimplification, and toward the end of the chapter, we will start talking about how this isn't quite exactly how things are, and that really there's a gradient. Some things are more ionic than others. You can have a purely covalent compound, and then there's sort of a gradient all the way up until the ionic ones. And so we'll talk about that later. And then we had the metallic, which we aren't talking a lot about now. You'll get into that more in Chem 1B, but we did want to talk about it a little bit. And the main difference here is that all of your electrons are delocalized. It means that one particular electron doesn't really belong to any particular atom. And so there's this kind of sheet of atoms and sheet of electrons all bonded together, which means that you can pass electrons through it. If you put an electron in one side, you can make it come out the other. And so that's why they're conductive. Now, this is sort of new. We didn't quite get into this before. And there's a little bit of background here that you sort of need to make sure you know from the fundamentals that maybe you glazed over a bit. So all of the processes that consume energy are called endothermic. So think back to your high school or 1P experiences and think about these words coming back to you again, right? For taking in energy, that's endothermic, bringing in energy. If you're releasing energy, you're throwing energy out, that's exothermic, right? Think exoskeleton on the outside. It's putting energy out into the environment. We're going to go really far into that in Chem 1B. Here we just need to be able to remember what's endothermic, what's exothermic, and the signs that are related to those. So we want to talk about the energy of an ionic bond. So think about, before I show you the next slide, which has a lot on it, what I said before about how we form an ionic bond. An electron goes away from one atom, it goes to the other atom, and then the plus and the minus are attracted to each other. So we have three kind of steps there. We have an ionization energy, the ion being, or the electron being pulled off an atom. We have an electron affinity, an electron coming into an atom, the other one. And then we have this other energy that comes from the attraction of a plus and a minus. And we have that energy. So three energies. And for it to be favored, we want it to be exothermic. We want it to give off energy. If we have to put a bunch of energy in to form something, that's not going to be favorable. So this is sort of the background for the next slide. Okay, so this is what I just said, all kind of laid out formally. First, this one. We have sodium losing an electron. We have an electron going away from the sodium. Now we have a word for that, right? We talked about it just last lecture. We called that ionization energy. An electron is leaving. So the only real difference here is, instead of talking about a trend, I just put a number on it. And I put a plus number on it. So it takes energy to be able to lose an electron. So this endothermic reaction in quotes. Now Cl is going to gain an electron. It's going to take an electron in. So that's, in other words, an electron affinity, right? Once again, what we talked about last time. And again, we'll just kind of give it a number now. So that takes a little bit of energy. And so that becomes 340, or negative 349. So these are just numbers for these specific things. Obviously not something that you would ever be expected to memorize. What I really want you to get out of this is the magnitudes. So 1B will go into more how to calculate energies and how to deal with them on a very mathematical form. I want you to kind of think about the magnitudes here. So we have a plus energy, we have a minus energy, so we have an endothermic, we have an exothermic, taking in energy, giving off energy. Okay, so once we do that, now we've switched to the electrons, right? We've taken away the electron from one and we've put it on the other. One took in energy, one released energy. Now we have sodium chloride, or we have sodium plus and chloride minus attracting each other. And that's favorable too. That's exothermic as well. So we get a negative 787. So you may want to add some little notes here, you know, if you've forgotten what designates an endothermic and an exothermic for signs. Pluses are endothermic, minuses are exothermic. So in order for this to be energetically favorable, you want it to be exothermic, which means, do you want a positive or a minus? Remember, endothermic, exothermic, and now we want this whole thing to be exothermic. So we want the whole thing to be negative. Well, what that means then is we need all three of these numbers to add up to be a negative number. So if we do that here, and we add up this, this, and this, you'll see that we get a negative 642 kilojoules per mole. So that's definitely exothermic, right? We have a negative charge. So it's lower, we're losing energy, we're releasing energy into the environment, and so it's going to be stable. So the idea here is that you want your electron affinity, and you want this value to be bigger than this one. If this is too large, or these are too small negatively, you have it's close to zero, you're not going to be able to form this. In this case we do though, because these added to this make a negative number. So your ionization energy has to be low enough to make this exothermic, and these have to be large enough to make it, these have to be negatively large enough. They have to be negative enough to make the whole thing negative. Now, this goes into why we tend to only form ionic compounds with metals. Something needs to have a low enough ionization energy to actually be able to do this. If this is too high, it's going to overwhelm these. If this was like 2,000, then it wouldn't be exothermic anymore. When you add, these wouldn't be able to get it into the negative line. So because of this, it's typically just your metals, right? Think back to last class. As we were on the left-hand side of the periodic table, where all the metals were, those were where our low ionization energies were. So this is where these numbers are kind of low. And so these numbers are able to overwhelm them. They're able to say, no, I don't care if you take a little bit of energy to do, we give off so much energy that it's still energetically favorable. So it's mostly just metals that do this because it's metals that have a low ionization energy. The ones on the right-hand side of the periodic table, carbons, oxygens, fluorines, all of those have such a high ionization energy. This number is so high, and go look at it. Pull out your table of numbers and see. They're so high that it's going to overwhelm it, and it's not going to happen. Okay. So now some Lewis dot symbols, in there's a little more formal introduction of them. They're gonna be how we represent our elements when we draw them out. And there's lots of different ways to represent them. Lewis dot symbols is one of the simplest and most used. So you put this symbol for the element inside, and then you put your dots around the outside. So for iodine, for instance, you have 7 valence electrons. You're not going to draw all your electrons, of course, just your valence ones. And then whenever you need to draw a bond, you do a line. You'll sometimes see people represent these, instead of a line, they'll put 2 dots instead and then just squish them close together, like this. That's fine, it's not wrong. And in here I like to do it to show you how we're switching electrons so that when we talk about ionic bonds, you can see it. When you're actually drawing these, it gets a little bit messy, and I would suggest keeping it like this and just putting the bonds. Just remember that every time you draw one of these lines, it's comprising 2 electrons. Okay, so now let's do some ionic bonds with these. If we have potassium and we have iodide, we are going to take the electron from potassium and give it to iodine, which forms potassium iodide with a plus and a minus charge. Lewis structures get a little boring with ionic compounds. They're a little bit better, a little more entertaining to use with covalent compounds. With magnesium, remember this was our example where we said, well, sometimes ionic compounds aren't going to form a 1-to-1 ratio. Sometimes magnesium might need to give an electron to 2 different atoms in order to make everybody happy. So magnesium says, well, I have 2 electrons that I need to get rid of, and fluoride says, okay, well, I'm only going to need 1. So they give 1 to fluoride and 1 to the other fluoride, or fluorine, forming magnesium fluoride. And the simple way of thinking about that was always, well, we need to balance the charges, right? If we know what our ions are, we know that magnesium likes to be a 2+, and if you forgot why, look at your periodic table. It's in the 2nd column. So you go to your periodic table, you see it's in the 2nd column, you know it needs to be a 2+. You go to fluorine on the periodic table and you say, okay, well, that has 7 electrons, so it needs to have a minus charge. So now, if I have an Mg2+ and an F-, I need to balance those charges. So that was a faster way of looking at it. Now, there was a trick to doing that as well, and it's to crisscross the charges. So if you had aluminum 3+ and oxygen 2-, you're going to take the 1 charge and bring it down, the other charge and bring it down, and then that'll give you a neutral compound, because 2 aluminums is 2 times 6, or 2 times 3 is 6, and then 2 oxygens, 3 oxygens, 2-, so that's a -6. So we have a +6 and a -6, so we have a neutral charge. And whenever you're forming ionic compounds, you need it to be a neutral charge. Now, there was a caveat to that trick, right? And that caveat was, well, what if you have the exact same charge of a higher number? Really, at that point, your best bet is if you have something that's a 2+ and a 2-, just know to put them together. Just know that it's a 1-to-1 thing. Or if it's a 3+ and a 3-, it's 1-to-1. But if you don't remember that and you don't pick up on it right away and you do the crisscross trick anyways, and you end up with Mg2O2, you have to reduce that down. Now, remember, only for ionic compounds do you reduce this down. For this, you have to make it MgO. You have to reduce it down. That's not true of covalent compounds, right? Covalent compounds might be N2H4, and you wouldn't reduce that down. Ionic compounds always have to be lowest whole number ratio. Covalent compounds don't. Okay, so now let's talk about some covalent compounds. So this is when you're going to be sharing electrons. So for instance, with chlorine, you can go ahead and you can take and you can share each one, this will share one of its electrons, this will share one of its electrons, and you'll form a single bond. If each element is sharing one electron, that's a single bond. And you can draw it like this or this. I highly suggest doing it this way though. And so that's how we're going to be representing all of our covalent compounds. So if I ask you to draw this, that's how you want to draw it. Here's a little bit more complicated example where now sulfur is needing to share electrons with multiple atoms in order to get what it wants. So it's going to share 2 with one oxygen, 2 with another oxygen to form sulfur dioxide. And so you can go ahead and whenever you are sharing 4 electrons total, 2 from each element, that's a double bond. And so you can write it like this, which gets a little messy. So I much prefer that you write it like this and actually form the double bonds. Now, for these simpler ones, that's fine to just kind of be able to write them out, but Lewis structures get pretty complicated. And so let's go through some general rules. And this is a good slide to keep with you as we go through all of the examples because we have a whole bunch of examples to do. And we'll follow through these guidelines as we go. Step 1, and this is the step that when you start getting good at them, everybody skips and it's a terrible idea. It's where you start making your mistakes. And you'll see I'm kind of lazy about it sometimes too, and I'll have to go back and do it at the end just to make sure I did it right. So add up all your valence electrons. In the beginning, this will help get you started. In the end, it'll check for your mistakes. So it's very important to do. Make a skeletal structure. So what I mean by that is you put your central atom inside, and then you put everything else around it, and you just draw single bonds. You connect them together. You kind of play connect the atoms. And you don't worry too much about lone pairs and double bonds and all of that. That just gets you started. So you know every time that you draw that line, that's going to be 2 electrons. Now you're going to have some electrons left over. So figure out how many electrons you have left over. Start with the number that you started with. Subtract out how many you had to use to form your single bonds. And now you know you have a certain amount of electrons left over. Put those around where you need to put them around. Now, octet rule, right? We're trying to get 8. So if you can't get 8, then you're going to have to do something else. So at this point, you do want to kind of be thinking, certain things don't follow the octet rule, and we're going to talk about what those are. These are some common exceptions, but there's going to be some other ones too, and we'll talk about why they are in a minute. But you're going to want to check for those so that you know, hey, this is an atom that typically does something that's a little bit funny, so let's go ahead and make sure that, I'm at least aware that it doesn't have to follow the rules. Maybe it will, maybe it won't. Now, if you can't distribute the electrons, if you try to put them around and you say, I have 2 atoms that I don't have enough electrons, where do I put them? That means that you need to start forming more bonds. Start putting double bonds, start putting triple bonds. A little note once you get good at them, if you're short by 2 electrons, you're going to have to add 1 more bond. If you're short by 4 electrons, you're going to have to add 2 bonds. So that's sort of a little trick to when you start getting good at them and you want to move faster. However many electrons you have left over that you're missing, you need 6, you're probably going to need to form 3 bonds. Now, this next part, and again, we don't know what all of this means yet. We're going to go through each of these in more detail as we do the examples. But this is just a good slide to keep with you while you're doing these, so you don't look at them and say, "What do I do? I'm stuck. I don't even know how to start this problem." This is your guidelines. They aren't hard rules. They change a little bit. Once you're done with all of that, and you theoretically have everything with octets, you theoretically have all of your atoms happy. Now you check your formal charges, and we'll talk about exactly what that is. We want them small. So when we get there, we want to minimize them. Now, the only way to really do these is to go through and do a ton of examples. And so that's what we're going to do. We're going to do a ton of examples, at which point we'll talk about formal charges, and then we're going to do some ones that break octet rules too. Okay. So first, we'll start you out with one that isn't too bad. We'll start with nitrogen. So our first step, and this is our error checking and making sure that we have somewhere to start from, is to count our valence electrons. So you pull out your periodic table, and you say, well, how many valence electrons does nitrogen have? Well, each one of them has 5. So we have 2 nitrogens, each one with 5 valence electrons, and so we have 10 electrons. We don't have a charge, so we don't have to add or subtract any electrons, and that's important to make sure you remember too. We'll do some of those later as well. So our next step then is to draw our skeletal structure. So we go through and we do that. Now we need to add in our electrons so that we satisfy the octet rule. Well, let's say we try to do this with nitrogen and we say, okay, well, I used up 2 electrons making that bond. So I have 8 left. So 1, 2, 7, 8. Okay, well, I'm short electrons, right? I can't give everything an octet. Nitrogen would need 2 more here, or 4 more here, and I can't do that. So that means I'm not sharing enough electrons. I'm short 4 electrons, which probably means I'm going to need to do 2 bonds, as sort of a good rule in your head to think about. So there's only one place to put those bonds, so I'm just going to put them there. Which means now I have 4 electrons left because I have 2, 4, 6. So I've used up 6, and I started with 10, so 4 electrons left. So now I'm set. 2, 4, 6, 8, 10. Always go back at the end and double check and make sure your electrons add up. And this is why it's important to do this in the beginning, even once you start getting good at them and you start just kind of whipping them down. At the very end, if you didn't do this, go back and do it real quick and double check it. Make sure that you've done it right. Okay, next one. Now we've made it a little bit more complicated. So now we have to figure out which one's going to be our central atom. Now, good rules of thumb for this, and there can be more than one central atom as well. The least electronegative element, that's going to be your central atom. And then everything else kind of goes around it. Hydrogen, how many bonds does hydrogen want to form? So all it has filled in its ground state is it has 1 s electron, one 1s electron. And so it can only ever form 1 bond. Hydrogen's not allowed to form any more than 1 bond. And so because of that, that's never going to be a central element. Oxygen can, but it's usually only if it's with things that only form 1 bond. So with all of those rules, that puts carbon in our center. Okay, so let's add up our electrons. So we have 4 from carbon. We have 2 from hydrogen. Well, let's write that this way. We have 2 hydrogen atoms, and each one of them has 1 electron. And from oxygen, we have 6. So we have a total of 12 electrons. So we put carbon in our center, and we put everything else around it. Now we try to distribute our electrons. So hydrogen doesn't form an octet, right? Hydrogen is the duet rule. It only has 2 electrons. So we have 2 electrons here and 2 electrons here. So that leaves us with, and 2 electrons here. So that leaves us with 6 electrons to work with. So let's go through and see if we can do this. Well, we have 2, 4, 6, 8, 10, 12. So we're set for electrons. Everything has an octet. So if you just walk away at this point, you're not going to get your points. And the reason for that we'll talk about in just a minute. But let's, for right now, see if there's another way we can do it. And after we talk about formal charges, we'll talk about why one is better than the other. So the other way that you can do this is by doing this. Forming a double bond here and putting your 2 oxygens here. Now, let's look at all of our octets and see what we have. Here we have 2, 4, 6, 8, we're good. 2, 4, 6, we're not good. And then our hydrogens are good. Here we have 2 and 2, so we're good. Our oxygen has 2, 4, 6, 8, so we're good. And now let's look at our carbon. 2, 4, 6, 8, so we're good with carbon. Here we didn't have enough electrons to do it. Here we do. So double bonds and triple bonds are a way to give ourselves extra electrons because we're sharing them. So this one's wrong, and this one is the one that we want to be using. Okay, Next example. And when you're doing these, you'll notice I've given myself an entire sheet of paper to do these on. That's on purpose. We're going to be using these for the entire rest of the quarter, pretty much all the way up until at least gas laws. So make sure that you give yourself just as much room as I did, and we're going to be adding to them. When we get to geometries, we're going to go through and we're going to put all of our geometries on. When we get to hybridization, we're going to go through and put all of our hybridization on. We'll do bond angles, we'll do polarity. We're going to just spend a lot of time with these sheets of paper. So 1 per sheet is about right. Any more than that and you start running out of room near the end of the quarter. Okay, now the next one. And this one gets a little complicated because now we have 2 central atoms. Now, luckily, people usually write these in a way that makes it a little bit easy to see what's going on. So you can kind of see here that we have BH3, NH3, and that's written that way on purpose. So you can sort of see that you have like a BH3 group bonded to an NH3 group. So first, count our electrons. We go to boron, we have 3. We go to nitrogen, and we have 5. We go to hydrogen. There's 6 hydrogens, and each one has 1 electron. So we have 14 electrons to work with. So now our skeletal structure. We can kind of see that boron and nitrogen are the only ones who can form multiple bonds. So they're going to need to be bonded to each other, as well as all the hydrogens. And so at this point, we say, okay, well, how many electrons do we have? 2, 4, 6, 8, 10, 12, 14. So we're good. Does everything have its octet filled, or for hydrogen its duet? Well, all the hydrogens are set. And then boron has 2, 4, 6, 8, and nitrogen has 2, 4, 6, 8. And so we're set there. Now, later on, we're going to talk more about exceptions, and we'll see that boron's actually one that a lot of times will have less than 8 electrons. A lot of times it'll just have 6, and it's fine with that. But here's an example where it actually does what most atoms do, and it has its 8. Okay, next one. Now we need to do an ion, so you have some practice doing ions. So we have XeF4, 4 plus. So count up all our electrons. So xenon has 8, it's a noble gas. And then fluorine has 7 each. So we have 4 fluorines, and each one of them has 7. So that would be 36, but it's a 4 plus charge, which means that we need to take away 4 electrons to give us 32 electrons. So it's a plus charge, so we have less electrons than the neutral atom, and so we minus the 4 electrons. So we have 32 electrons to work with. So we put xenon in our center. Fluorine, never allowed to break the octet rule, and we'll talk more about that in a minute as well. So fluorine is ever only going to have 1 bond. So whenever you see a hydrogen or a fluorine, only 1 bond, it can't be a central atom. So when we go through and we draw these out, we know fluorine can't have more than 1 bond, since I just told you. So really all we can do at this point is add in our lone pairs and hope everything works. If not, we'll have to add some things to xenon. So if you count all of these, 2, 4, 6, 8, all the way around, what you see is that we do in fact have 32 electrons. So we're set, we're done. We don't have to do anything else with this one. Okay. Now our last and most complicated one for right now. And this one we won't actually even be able to finish until we talk about some other things. Okay, so N2O. So this one's kind of not as simple as the other ones, right? And we'll see why in a minute. So first of all, most electronegative element here is oxygen. So nitrogen's going to be in our center, one of our nitrogens. So we can set up our central atom as being nitrogen. And we can put a nitrogen on each side. excuse me, a nitrogen on one side and oxygen on the other one. And then we can draw our skeletal structure. Now, if we try to give everything an octet here, first we're going to need to count our electrons. So you'll see that we have 5 electrons from each nitrogen, and we have 2 nitrogens. We have 6 electrons from our oxygen, leaving us with 16 electrons. If you try to make your octet here with just going and filling in your elements or your electrons, and we just, kind of fill in, you notice we can't do it. We don't have enough here, right? We would need 4 more electrons. So if we're short 4 electrons, how many bonds do we need to form? We need to form 2 bonds. Okay. Well, where do we put those bonds? Now we have some options. When we had to form 2 bonds with that N2 group, we didn't really have any options, so we just sort of put them in between the 2 nitrogens. Here we have options. So I have 2 bonds that I need to form, so I could just put 1 bond on each group. I could put both bonds to the oxygen, or I could put both bonds to the nitrogen. And let's go through and fill in our octets at this point. So we have 2 here, so we need 2 more. This nitrogen's set, 2, 4, 6, 8. This oxygen needs 4 more. We count up our electrons, 2, 4, 6, 8, 10, 12, 14, 16, we're set. We move down to this one. Now this nitrogen needs 6. This nitrogen again is all set. And this oxygen's going to need 1. This nitrogen needs 2. And this oxygen needs 3. We go through and count, 2, 4, 6, 8, 10, 12, 14, 16, we're good. 2, 4, 6, 8, 10, 12, 14, 16, we're good. Okay, well, which one is it? So all of them follow all of the octet rules. All of them have the least electronegative element in the center, so which one do we do? This is where that very last step on the slide comes in. Calculate formal charges. We don't really know how to do that yet, so let's learn how to do that, and then we'll come back. So there's an equation for this, and once you start getting good at it, you're going to want to do it more sort of internally and be able to quickly check all of your formal charges. You don't necessarily always want to be filling into this equation, but for the moment, it's a good thing to start with. So your valence electrons, so you start there. So for nitrogen, it's 5, oxygen, 6. If you ever forget, you just go to your periodic table and count over until you get to the element where you're at. Now that's your starting point. Then you subtract the number of electrons that the atom that you're talking about in your whatever you're looking at. What I kind of always think of it as which ones they actually own. So which ones are sort of their electrons. So the way that that's calculated is the number of electrons that are actually in that it has all by itself. It's lone pairs. So you're subtracting away all the electrons that are inside the lone pairs, and then half of the bonding electrons. So if you have a bond, one of those electrons belongs to one element, and one of those electrons belongs to the other element. So for accounting purposes, you always think of half of the bonded electrons. We'll do some examples that'll make that make more sense. So let's go through and assign formal charges to all of the Lewis structures that we did. And then when we get done with them, we'll be able to actually go through that last harder example that we did and decide which one it actually is, which Lewis structure is actually correct. So just sort of starting over on our Lewis structures. Again, you're going to want to keep them handy and do this quite a bit throughout this next little bit of the quarter. Okay, so our first one. So what is our formal charges on each nitrogen? So we go and we say, well, and formal charges are going to be atom specific. So it's for each atom in the molecule. Now, in this case, they're going to be the same, but we can still calculate them for both. So how many electrons does nitrogen have, valence electrons does nitrogen have? So you go to the periodic table, you count over, and you see that nitrogen has 5. Now you have to decide how many are its own. How many does it have in this structure? And you're going to subtract those away. So anything in a lone pair is its own. So it has 2 from the lone pairs. From the bonds, it only gets 1 from each bond. So 1, 2, 3. So you have 5 valence electrons minus 5 is 0. So this nitrogen's formal charge is 0. Now, if you go to the other nitrogen, the exact same thing happens. It has 5 valence electrons. It has 2 electrons that are in lone pairs, and it gets 1 from each bond. And so that nitrogen is going to be plus 0 as well. Next one. So now we can go through, we can talk about each one individually. So let's start with the oxygen. So how many valence electrons does oxygen have? It has 6. And we're going to subtract away anything that are in lone pairs. So 1, 2, 3, 4. And any of the bonding electrons, but only 1 from each bond. So 1, 2. So we have 6 minus 6. So the oxygen's charge is 0. Carbon, we go to the periodic table. We say how many valence electrons does it have? And it has 4. So we subtract away anything. In this case, there's no lone pairs, so we don't have to count any of those. And it gets 1 from each bond. So 1, 2, 3, 4. So we have 4 electrons there. So its formal charge is 0. Now we need to talk about hydrogen. Hydrogen has 1 valence electron. And it gets 1 from each bond. So its formal charge is 0 as well. And that would be true of the other hydrogen as well. So those are all our formal charges for that one. Next one. So now this one, when we go through, it's going to be a little bit different. We'll start actually getting some formal charges. So let's start with the hydrogens. Hydrogen gets 1 valence electron. And it's the same for each of these hydrogens. It'll get 1 from the bond. So every one of the hydrogens on here follow the same rules, and so they're all going to be plus 0. Now let's talk about the boron and the nitrogen. For boron, how many valence electrons does it have? So you go to the periodic table, and you see that it has 3. Now, if you come here, and we count electrons, no lone pairs, so don't worry about those. Gets 1 from each bond. So 1, 2, 3, 4. So boron has a -1 charge. Now, nitrogen, if you go to its it on the periodic table, you'll see that it has 5 valence electrons. And you count around 1, 2, 3, 4. And so you have a +1 charge on nitrogen. Now the xenon tetrafluoride. So for each of the fluorines, because again, they're all going to follow the same rules, so we're only going to do it once. They get 7 electrons from the periodic table, valence electrons. Now here, each one of them has 2, 4, 6 that are in lone pairs. So those are the fluorine's lone pairs. It's not sharing them, it's not doing anything with them. So it owns all of those. Now for the bonds, it just gets 1. So we have 7 valence electrons minus 6 electrons that are in the lone pairs and 1 electron that is in the bond. So each of the fluorines are going to have a 0 charge. Now we move on to the xenon. It's a noble gas, so it's in the 8th group. It has 8 valence electrons. And we subtract 1 from each bond. 1, 2, 3, 4. So we subtract 4 electrons. So it has a +4 charge. So as we're going through these, you should notice that we're counting electrons very differently depending on what we're doing. When we were counting for octets, we counted everything, right? For xenon, we went through and we just said 2, 4, 6, 8. Xenon has an octet. Fluorine has 2, 4, 6, 8. Fluorine has an octet. That's very different from when we do formal charges. With formal charges, the bonds only count as 1 for each atom. So fluorine, we only got to count that as 1 electron. For the sake of octets, you count it as 2. Okay, so now we can move on to our last one, which was a bit more complicated. And we weren't actually able to finish. Okay, so we had this. And we said, well, I don't know which of these 3 to do. Now we can actually go through and we can figure this out. So let's do that. Let's go through and put formal charges on everything. And I'm going to do this a little bit quicker this time and do it a little bit more like how you should be doing it on an exam, and how after maybe about a week of practice and a week of homework you should be doing it. So we look at oxygen and we say, how many valence electrons does oxygen have? Well, it has 6 of them. How many does it have in lone pairs? 4. Okay, so we're down to 2 electrons at that point, and then 2 here. So oxygen has 6 valence electrons, and here it has 1, 2, 3, 4, 5, 6. So 6 minus 6 is 0. Let's actually switch colors just to make it a little bit more obvious. +0. Now nitrogen. Nitrogen has 5 valence electrons, and here we have 1, 2, 3, 4. So we have 5 minus 4 is equal to 1, and it's a positive one. Now here, nitrogen has 5 valence electrons, and here it has 1, 2, 3, 4, 5, 6. So 5 minus 6 is minus 1. So again, when you're practicing at home, do it the way that, in the beginning, do it the way that I've been doing it up until now. When you get a little bit on a roll with it, this is kind of the fast way to do it. This is how you want to be able to do it for the sake of, checking your work quickly without having to waste too much time. Okay, let's do the next one. Here, we have oxygen normally has 6 valence electrons. Here it has 1, 2, 3, 4, 5. So 6 minus 5 is a +1. Over here, nitrogen normally has 5, and here it has 1, 2, 3, 4. 5 minus 4 is +1. Here, nitrogen normally again has 5, but here it has 1, 2, 3, 4, 5, 6, 7. 5 minus 7 being -2. Okay. So just going through, putting formal charges on everything, and then this is going to help us decide something when we're all done. Down here, oxygen normally has 6. Now we have 1, 2, 3, 4, 5, 6, 7. We have -1. Here, nitrogen normally has 5. 1, 2, 3, 4. So 5 minus 4 is 1. +1. Over here, nitrogen has 5 valence electrons, and here it has 1, 2, 3, 4, 5. 5 minus 5 being 0. Now, as a good check, we need to go, this is something you kind of want to do in your head for everything. You don't necessarily need to write them down. If I ask you to write down a Lewis structure, you don't have to put in formal charges. If you have something that's an ion, actually, like this, if you have something like an ion, it's not actually correct unless you put the charge somewhere. But you don't have to put the charge on xenon. You can just put brackets and put the charge, and that's fine. That's just as correct. Something like this that doesn't have a charge, you don't have to put the, you don't actually have to put the formal charges unless I ask for it. You should do it in your head anyways, though. Now we have to decide which one's correct. So if we look at these, a good check first is to make sure that all of our formal charges add up to whatever the charge is here. So charge is 0. So this one adds up to be 0, this one adds up to be 0, this one adds up to be 0. So we've done our formal charges correct, we've done our Lewis structures correct. Now we have to decide which set of formal charges is the best set of formal charges. And so if we go through and we look, we can say, well, this one has a -2, a 1, and a 1. This one has a -1, 1, 0, -1, 1, 0. This one has some really high formal charges, and there's no reason for that. 2, 1, 1 is acceptable if there's no other option. You will have formal charges of +4 sometimes. We saw that with xenon. But if there's another option, you don't want to do that. So we're going to get rid of that one right away. That one's not going to be right. So now we have to decide between these two. So they're basically the same. Our central nitrogen has the same. But now here we have a -1 on the nitrogen. Here we have a -1 on the oxygen. So we have to figure out which one's better. So for this, we need to kind of backtrack to what we talked about earlier today or last class, where we were talking about electronegativities. So when we're talking about electronegativities, we're talking about the amount that an atom is willing to pull the electron density toward it inside of a bond. So this is kind of exactly the situation. And something like oxygen is more electronegative than something like nitrogen. So if the electron density is going to be shifted one way or the other, it's going to be shifted so that the more electronegative element, the one that's pulling the electron density toward it, is going to be the negative one. Because, well, it's more electronegativity. It has more electronegativity. It's pulling those electrons toward it more. It's going to take the negative charge, not nitrogen. So this one is going to be correct, because oxygen is more electronegativity, or more electronegative. So you always, if it's possible, and keep this in mind, if it's possible, you want to put your negative charge on your most electronegative element. That's not always possible. For instance, this one again. In this one, we had a plus. Oh, I guess we didn't have a negative charge. Never mind. So draw out CO for fun sometime. Draw out carbon monoxide. And you'll see that you're forced to do the opposite of this. And you don't have a choice, and that's fine. If you don't have a choice, you don't have a choice. But in something like this, we do. We can choose to put it on the nitrogen by drawing it that way, or we can choose to put it on the oxygen by drawing it that way. So this is the more correct way. Okay. So now, moving on a bit. More in detail about breaking the octet rule. So I've been sort of alluding to this and talking about it, but now we're going to go into it in a little bit more detail and talk about exactly when we can and can't do this. So your second period elements, they're not going to do this. So that second row of the periodic table, well, and of course hydrogen and helium as well. Hydrogen, helium, and then lithium up through neon, they're not going to do it. Do not ever have 10 electrons off fluorine or an oxygen or nitrogen. You will just get it wrong. There will be no partial credit for that. You'll just have it wrong. Now, third period and lower, you can do that and it's fine. That's not a big deal. There's some that are going to do it more than others, but not all of them. Now, the third period element can do it where the second one can't because of the fact that they have some d orbitals sitting right there. So the d orbitals are right there. They're able to be used for bonding. You can use them for bonding. You can use them for hybridization, which we'll talk about later next chapter. And so anything below, third row and below, can do it. Second period ones, do not do it, ever. Some of them are going to have a lot less than 8, and they don't have to, but they can. Theoretically, anything could have less than 8 electrons, but that's not necessarily normal. For beryllium, aluminum, and boron, it's pretty normal. If you see one of these and you can't fill the octet, don't worry about it, just move on. Something like carbon and oxygen, you're going to probably fill the octet. They're seldom going to break the octet rule. It's not something that you're going to ever see in this class. Where these elements, they do it all the time, so get used to these elements breaking the octet rule on the low side and having less. As far as having more, that falls into the category of sort of a lot of these that I talked about. Sulfur, phosphorus, xenon, chlorine does it a fair amount. So anything third row and below can do it, but these are sort of your common ones that actually do it all the time. So we'll start and do some examples of this now, and then do some more next time. Okay, so we'll start with SF6. So our central one is sulfur, since we can't really do anything else. We can't put fluorine in the center. And so when we go through and do this,